start going this side and SiO2 will keep forming upwards. Okay. The advantage of this SiO2 is that boron now cannot leave on the upper side because SiO2 will block it. Okay. This is a natural thing happens, so great for us. In process, the boron starts going down, diffusing down, and oxide stops it going out. Otherwise by diffusion it can go either side. Is that clear? Diffusion is a random process, but upper one will now stop. Once I cleared this, I said I need contact to be done. So I said, okay, I have this so-called your oxide done. There are also another oxide. This may be of same thickness, it depends on the time. Okay. But now I do, in this P region, I want a contact. So I said, okay, use second mask. Now the second mask is done. Let's say this was my pattern, which is the first mask pattern. This, which is this. Okay. I want to make a contact inside that area. I don't want contact here, I want only contact to P. Is that clear? So I must see to it that the window is open in this P, so it almost goes into the center. So I have the next mask. This is not this pattern actually will be visible on the top, and my next mask will be something like this, which will go inside that. The reason we keep this, during this second mask printing, the first pattern is visible on the silicon because of the thickness change, and when I align the second mask, that window should actually get into the earlier window. So please remember, this window will be visible to me from the top. Okay, so when I put the next mask, everywhere, this is not one diode, there will be millions of diodes on the wafer. So everywhere this second window must get inside that. So I keep some leeway, otherwise what will happen during fixing, this may move. If they are equal, what can happen? I may get pattern something like this, so I will have a smaller window on one side in some places. So I want to align, this is called alignment. Okay. So the second mask is to be aligned with the first, therefore size has to be slightly smaller, so that everywhere I can see pattern inside. This is I see through a microscope. This is a mask aligning system, typically cost these days 70 to 80 lakh rupees, which is not the best of aligners. Okay, so once I have this mask created, so what do I do for second mask? Again I coat it with resist, NPR, put this mask, expose, this black portion light will not go to the resist below. So I have a resist here. This is the area where resist will remain soft. The rest portion, so I develop the resist and then I etch oxide again. This is my resist, which is hardened resist because, this is light did not go, the rest everywhere light went, so that became hard. Hard means unetchable in normal etchants. So when I did etching of SiO2, I have a window which is now inside P region. Is that correct? So the second mask opened the window. One interesting feature I am never showing you, but remember, silicon is not selective. If the top surface is getting oxidized, same time the lower one will also get oxidized. However, when I will etch this, that will etch away automatically, the whole wafer will get backside etching. So I don't show you. If this oxide is etched, same oxide will come here. So when I etch this oxide here, the lower one will also go up. Because there is no mask there. I repeat. When I grow this oxide, silicon cannot say I will only have top layer oxidation on both sides. When I open a window for this, I will etch this oxide by masking. When I am etching this oxide, this is not masked, lower portion is not masked. So when this oxide will go, this lower one will also go. Okay, so lower portions we never show, but actually always everything happens when the top will happen in the down also. But since that contact right now I don't need side, but I remember there is no oxide here now. I open during this, I will also have another oxide here. Yeah, but wafer is kept like this, mask is placed on the top. Okay. So light, light is always vertically. So when the light is shining, nothing happens. And there is no resist there on the back side. Resist is on the only top. Is that correct? So the lower oxide is always there, but when I etch upper oxide, same thickness of oxide will go from below when I etch it. However, this was also during this process, I will also have another oxidation because I am doing SiO2. This process oxidation is going on. Okay. But this, when I etch this oxide will go. Okay, so on the bottom we normally don't show anything, but the process happening above takes care of bottom place. So now I need metallization. So the next thing is metallization. So what I do is, okay, so I'll show you now. This is my window, this is my P, this is my oxide, and resist has been removed now. Resist has been stripped off, removed now. So this after, then as I say stripping of resist, every masking step is over, etching is over, you remove the resist. And now this is the situation. This is P, this is N. So I actually evaporate metal on this side. This is called metallization. Normally aluminium, which is one of the better conductors, which is the best conductor? Best electrical conductor. Copper. ना पता होना ही चाहिए. Copper is one of the best, or rather the best, both thermal as well as electrical conductor. That's the best part of copper is, it is best thermal conductor and best electrical conductor. Please remember, both are not true in all cases. Is that clear? So some things which are better thermal conductors are not necessarily good electric conductors, or even they are insulators at times. Whereas we need both. Copper has a problem. What can be the copper goes into silicon. What it can do? Copper is a second group element. What we did sometime earlier for last lectures, something we added to fill something. What did we do? We said you add gold to create levels in the band gap. What are these called? Traps. Copper creates two traps. Okay. So what will it kill? The lifetime. And in many cases, as I say, bipolars require larger lifetime. So copper is called poison for silicon. Okay. However, in 2098 onwards, IBM, Texas Instruments, even Intel, that little a year later, started using copper as interconnect. Till that time, since 60s to 98, we were only using aluminum. Okay. 98, first time people thought, why not use copper? All that was done that, okay, copper should not get in touch with the silicon. So there was a cladding given to you between copper and silicon, so that copper does not go into the silicon. However, the whole interconnect line was made out of copper. That clad technology was very difficult in early times, and we could never use copper in. In fact, in the lab, nowhere even copper material is allowed to be in. Okay. So that's very, very risky for us to get into the lab any copper. Now, as I say, I deposit copper. Assuming right now we have aluminum, old ones, how do I deposit metals? By evaporations. There are many techniques. One is evaporation. If you start using aluminum in air and heat it, what will it do? It will evaporate. But what is the problem with evaporation in the case of air? It will oxidize. Alumina is a good insulator, in fact. Alumina is a good insulator, Al2O3. Then I don't get aluminum. So where should I oxidize, deposit? In vacuum. So the system which are built to deposit metals is a vacuum chamber, inside which there is a huge pumping system goes with this, lot of things, and we keep our wafers, we keep our source, tungsten source, aluminium wires, silicon is held here like this, and if I now heat this in the vacuum, typical vacuum should be 10 to the power minus 6 torr, centimeter of mercury, and then what is the advantage of vacuum? Can you think? There is no oxygen is one. 10 to the power minus 6 means very residual gases, very small amount there. So what is the advantage of vacuum otherwise? In air, there is some quantity called mean free path is very small. Okay, it's proportional to 1 upon P. So smaller the P you keep, larger is the mean free path. So what is the advantage of larger mean free paths? The aluminium atoms will go vertically upwards before they collide each other. In air, that was also a problem, they scatter. Okay. So here, they go actually vertically up. So you know how much thickness by time or by measurement, how much thickness aluminium is you are depositing. This is called, there are various techniques, this is called filament evaporation, then there is the electron beam can shine on aluminium and heat it, called electron beam evaporation. The third process is sputtering, and CVD some other day. Okay, many bases. Simplest way I said deposit. But aluminium will get deposited on every place, on all layers. But I need only contact in this region. So what should I do? I must etch aluminium from the rest portion except where I need only this much. That is, it covers the window. Okay. Again, now remember, it should be larger than this because any case, if it is exact of this kind, I may get this area. So I want to protect that all areas get covered. So the next mark should be what? It should be larger than this, or maybe of same size, or even third mask should be even covering all of it. Is that correct? So that metal sticks. To do this, what should I now do? The third mask, which is what kind it should be now? I want to retain metal and etch this part. So if I deposit my photoresist, what should be the kind of mask I should use? In this was clear areas. These portions were dark. Now I want to retain the areas in the center. So light should go there or not? Light should go there. So a window should be clear and this should be dark. So these masks are called dark fields. Larger area is darker, windows are opened. Okay, clear. So if I now put this mask on this, which has black portions here, black portions here, black portions here, the light will go from here, okay, will harden the resist in this region, okay. Then I will etch out the aluminium from the rest of the portions. Is that correct? Then I remove the resist and I have a final diode with me. This is my P, this is my N silicon. And same way, I use the back contact full size. During the evaporation, first evaporation, I will immediately invert the wafer and coat full wafer from the back side. Okay. So I have now, this is my oxide. And this is my metal. Okay, this much. One contact is here, one contact, you can take contact either way. So this is my P, this is my N. So you have a diode created. How many masks required to create a simple diode? 3 masks. As I said, to make an integrated circuits in CMOS, you require around 24, as large as 30 sometimes, or Intel process is 27. Now what is the problem of larger number of masks? You have just seen for 3. I have to keep aligning all of them. Now these features are big enough for a diode, but in normal case technology is now 22 nanometers. So for a smaller dimensions, the gap between this is very small. The alignment has to be very perfect, otherwise half the chips will not work. So that's why aligners are very important process. It is called lithography. This is called lithography. Using light, we say it is photolithography. If the resist which is exposed by electron beams, called electron beam resist. It's called polymethyl methyl acrylate, PMME, someone wants to know. So this is exposed by electron beams and it hardens or softens, depends on the kind of PMME I use. Is that clear? So how do I make a diode? Yes. Okay, since this portion has the resist, which is because of the window I opened is clear, this portion of resist becomes hard. Is that correct? The rest of the aluminium does not have resist because that was developed by me. So when I dip this, and of course then I also coat the backside with a resist because I don't want to etch backside metal. Or even you finish this and then coat, that also is possible. And then you etch the aluminium, so this aluminium will go. Then strip the photoresist, so you have the contact left only a small area. Okay. This is one, this is the cross section. And the contact, you can see the aluminium is making contact to P. Is that clear? So this is a contact to P, this whole backside is a contact to N, so you have a diode which essentially is this. So I made a diode using a PN junction, so I can make a NP junction. What should I do for NP? Start with P substrate and impurity, which impurity I should use? Phosphorus, normal cases, or arsenic. Arsenic is much better. Okay, I'm not kidding. There is a word, something called solid solubility. Have you done any course in material sometime? The word is solid solubility. What is it? The amount of solid, other solid, which can get into one solid without disturbing the lattice, the amount which concentration it can receive is called solid solubility. Arsenic has larger solid solubility compared to phosphorus by at least 5 times. So what it means? Much more arsenic concentration can be pushed in compared to phosphorus for similar processes. What is the advantage of that? Okay, that's what we are going to do. In real life, this will be plus stands for higher dope, minus stands for lower doping. No other marker means normal doping. 10 to the power 15 to 10 to the power 16 per cc is called normal doping. Anything below 10 to the power 14, 13, we call it minus. And anything beyond 10 to the power 17, we call it plus. And if it is greater than 10 to the power 18 or something, we call plus plus. If arsenic has 10 to the power 21 per cc as its solubility, this N plus can come closer to this value. So larger the N plus or P plus, which will make the device will have better characteristics. Junction is not PN junction, either P plus N junction or N plus P junction. Is that clear? Or N plus plus P junction if necessary. And we'll see now theory, why do we want to dope larger on N plus or P plus. Okay. In case of a transistor, if you look at NPN transistors, which is heavily doped region, this is your base, this is your emitter, this is your collector. So emitter and collector are differently doped for N's. Is that correct? One is plus plus, heavily doped emitters. Okay. Therefore it is not same as collector. Okay. If you use the transistor in opposite way, the gain is very low comparatively. If you do theory wise, collector can be also called emitter because it can, NPN is other side also. So you can think that NPN either side is a transistor, yes, but when N plus plus PN transistor is used as emitter based collector, the gains are higher compared to when you use NPN plus plus. Okay, we'll see theory why it happens. So I'll use either arsenic, but then why not use arsenic often? Okay. The gas which is still going on, the problem in Bhopal, no, still compensations are not provided. The gas which was used then was what is called phosgene. Okay. Now that gas, what we call toxic level, which is tolerable, is around 100 parts per billion. In 10 to the power 9, 100 parts. Phosphine, which is another phosphorus based gas, which is around 10 ppb toxic level allowed. And arsine is less than 1 ppb. So, and another problem, phosphine smells like a rotten fish. So if phosphine leaks in my cylinder, I may run for my life. So there is some time before I run. Maybe I still wear everything, gadget, oxygen, but I may still run for it. But in arsine, it doesn't smell. If it leaks, I am no more to know what has happened. Okay. So that's what we say, that why we are very worried about arsenes earlier days, because we didn't have enough protection in clean rooms we have. So we never used to touch arsene. I was the first probably known person in India who actually opened an arsene cylinder. Took all the courage to do that and have doped arsene in my case. So don't worry. The point is that if you take precautions, life can be done, anything can be done. But if you just run through in our lab, you will die in no time. Okay. So VLSI is a very funny area. Okay, so is that clear? This? Yes. This is resist. Resist, that much is developed, the rest is hard. To make a window for an NPR, you should have a darker area where light cannot go, so resist can be developed there. Okay, so if I have another resist which is called PPR, positive photoresist, what should be its property then? What is NPR? It's a open link resin, open carbon chain link resin, and when I shine light, energy, it links, okay, cross-linking. What should be PPR then? It's already linked, okay. When I shine light, it breaks, okay. So when I shine light, that is etchable. Otherwise, it is unetchable. What should be the mask kind then? This was a clear field mask, so if I am using PPR, it should be a dark field mask with an open window, because there only it can be etched. Photoresist will remain soft there. Light should go there, light should go there so that the resist becomes soft there. So opposite mask can create using PPRs. Is that clear? Using PPRs. The dark field should be clear field should be dark field for opposite field, because PPRs are ones which are already linked, and when shine light or when they receive energy, they actually open up. These are very long 32 carbon hydrogen chains, which are long chains, and when they form benzene structures, number of them, then they become very much difficult to etch. Because as I say, stripping is required. Strong nitric acid, which is called fuming nitric acid, etches even this. Okay, so don't worry. Aqua regia doesn't do. This is very funny. Aqua regia was always called it can etch everything. This resist is not etched in aqua regia. Don't add any HCl to that. Actually put strong 58% full nitric acid fumes, it will remove resist. Okay. The problem is something very interesting when the metal is there, because if that metal also can go, some tricks have to be used. Okay, so we see today how to make a diode, and by additional process step, what can we do? A transistor, what should be there before this metallization? What should I now do here? I use similar mass and make N plus inside. Then I need a contact here, and contact here to make 3 contacts. Okay. Keep doing mask. Transistor requires 6 masks. To create an NPN. Okay. Mass transistor also requires 6 masks. But in 4 we can make some rudimentary MOS. But normally we require 6. Okay, so this is something which is not taught normally by me in this course, but I thought your batch may never learn technology anywhere, so at least you should be exposed. Okay, what is all this VLSI technology is about? Okay, so let's start with what we were really intending at. As I said, this was additional feature for you. Okay, now let's do a theory of PN junction, which is what we are more interested in this course. I have a region which is P, and I have a region which is N. If I draw a band diagram for each, I have for P, okay, this EI of course is same, ECP, EVP, EVN, ECN, small, and this is EI. You need not connect. Where will be the Fermi level for p-type? Close to the valence band. So there is EFP. Fermi level on the p side. For N side, Fermi level will be closer to the conduction band, EFN. Is that okay? So if you have two separate materials, P and N, this is the band diagram. But now we are trying to connect E and N together. So if I start connecting the junction, connecting to form a junction, this is my junction, this is my P, this is my N. As soon as I connect, now I figure out, let us say P has concentration of Na and this has concentration of donors as in D. So P's of P is how much? Na, if all are ionized. Holes on the P side is same as acceptors concentration you put there, if all are ionized. And how much will be N's of P? Ni square by Na or Ni square by Pp, whatever it is. Similarly, N's of N is in D and P's of N is Ni square by N. Typically, normal Na and D will be 10 to the power 15, 16 kind of concentration, that is per cc. Ni is 10 to the power 10, so we are still 6 orders above. Is that clear? We are still 6 orders above. So if I have a p-type material, I have very few electrons. If I have n-type material, I have very few holes. So as soon as I touch, the holes on the p side, see on the n side, very few holes. We have large holes and has pure holes. So what it tries to do? Because it doesn't like that the other side should be so poor. In India it doesn't happen, but normally it should happen. Okay. Now why it doesn't happen, we'll show you what is it now, why it's not happening. Here also it's not happening. So holes actually starts, let's say hole starts moving from P side to the N side. By the same argument, electrons on the N side are larger and electrons on the P side are smaller. So what will they do? Electrons will diffuse from N side towards P side. This process is called diffusion. They will diffuse. But whenever electrons leave N-type or holes leave P-type, what they leave there? Ions. They will leave ions. So if I expand this or if I remove this area, where from the electrons first will go, which are very close to the junction. So as soon as holes left there, acceptors appeared. Wherever electrons left, donors appeared. Is that clear? On the N side, we have donor layer. On the P side, we have acceptor level. Okay. These are not moving ions. Is that clear? Clear. These are fixed in the lattice. Is that clear? So they don't move. Since most of the electrons, right now we assume there are no electrons and holes in this region. Those were already gone, those on the P side already holes gone. So in this region, there are no free electrons and holes. Assumption. Reality, how much we can find that. Very small will be there compared. So we say, this is equivalently saying something like this, only this portion I show you. These are acceptors, these are donors, this region does not contain electrons or holes, so this region is called depletion region. Why? What is being depleted? Free electrons, free carriers. And let's say this width right now, say W0 is this much. However, if I call this junction as x is equal to 0, this boundary I call xp0 and this boundary I call xn0. Is that clear? On the P side, opposite sign ना, because वो 0 बीच में लिया है. So how much is W? So the thickness of ionized layer on the P side plus thickness of ionized layer on the N side, total is the depletion widths. Is that correct? Depletion widths. Now once this depletion width, and ahead of course there is a P region, ahead there is of course N region. On this side, N and P side, the semiconductor is always having which things it is always satisfying? In this they are not satisfying. What is not satisfying? Charge neutrality may not be satisfied for holes and electrons but always be satisfied for ions. Outside this, there are electrons and holes both sides and charge neutrality always holds. Since there is no current flowing because I am not connected anywhere, the neutrality says there should not be any voltage drop across N region and P region because there are no carriers moving and there is no voltage drop, IR cannot create there. Now if that is so, this depletion layer, I certainly look as if, I'll rub this to just show you, this is a positive contact and this is a negative contact. And this will be maintained because let's say some reasons they recombine which they cannot, then holes electron will again come from both sides and will make this constant. Okay. So this depletion region is giving me equivalent of a battery here. Battery has an ionized charge, that's what the battery essentially means. Any whatever electrolyte is ionized, that's why you say called battery. This is a battery here. Why it is created? Because ionized accepted donors appear, free electrons left them. This battery creates an electric field in which direction? Positive to negative. Is that correct? Holes move in which direction of electric field? Same direction of the electric field. Electrons move in the opposite direction of. So now these electrons which are here and holes which are here, can they go across? Because this electric field will not allow additional holes electrons diffusing through. Is that clear? This field is therefore called built-in field or V0 or total potential. Okay. Built-in potential or built-in field which it creates. Is that clear? So as soon as diffusion starts, we will create electric field. And this electric field will then not allow additional holes. Otherwise, normal diffusion, what should you do? P should be throughout same, N should be throughout same because there is diffuse till they are equal. Is that clear? That will stop. Is that correct? That will stop because there is a built-in electric field already present there. Okay. Before we go ahead, I already said there is no voltage drop here or here, but let's say I make a contact here. If I apply a voltmeter across this, would you see a deflection? I repeat, problem is this. Is that clear to you? I have created a battery, so if I apply two terminals, of course there is no drop here anyway. So if I measure across this, I should have seen the V, but I don't see any deflection. Okay. So that means this battery is some kind of a quasi or false battery sitting there, but if it is not there, this would have really gone infinite. They would have gone, all holes electron would have diffused out. That have not occurred. Obviously there is a built-in field. Why it did not measure? 2 minutes later or maybe tomorrow. Okay. So this issue that whenever diffusion will occur in PN junction, a built-in field will immediately set in. And if this is electric field, let's say this, something this will be equal to integral E dx over the range which you are talking. What is the range in this case? In this, and this voltage is called built-in voltage. This voltage is called built-in voltage. Is that correct? So our aim should be then, what first I should find out? The electric field. If I get electric field across the junction, then I can always evaluate the voltage across the junction. Is that clear? Now in the band diagram, what is it translating into? You say, okay, it will create a built-in voltage or built-in field, or built-in voltage means energy change. QV0 is energy. Is that correct? So if you say there is a built-in voltage between P and N, obviously there must be energy change in P and N, and it should show us in band diagram. So let us see, go back and look into this figure again. थोड़ा सा इसको you draw again. I have duster. I can do that in no time, but you don't have a duster, so you redraw this figure again. Okay. Let us start thinking. In this semiconductor, if I don't connect this, no connection here, even in voltmeter it's so infinite impedance, so it doesn't pass any current. But right now no currents here. If there is no current, what is the theory in Fermi level we suggested? The Fermi level must be constant across. Is that correct? So between P and N, the Fermi level must align because there is no current between P and N. Okay. So if that is to be done, let us say this is my junction. This is my junction base. Okay. So I say Fermi level along, okay, this is the junction area. Fermi level on the N side must align with the Fermi level of P side. Is that correct? Because you say no current, dEF by dx is 0, EF is constant. If EF is constant, we know the carrier concentration of electrons and holes is related to with the Boltzmann equation. What are those equations? P is equal to NV e to the power minus EF minus EI by KT, or N is equal to NC e to the power minus EI, or first one was EI minus EF, next is EF minus EI by KT. Since I know difference between EI and EV or EC decides the hole and electron concentration, obviously for the same concentration ECN must be here, band gap cannot change, so EVN must be here, and your mid gap EI should be here. Is that clear? Because Fermi level has to align when in steady state or equilibrium no currents. Okay, no currents. So obviously EF must align. EF must align. If EF has to align, the band must, N type of band must be lower than that of P type, so that EF can be aligned, and essentially there is a connection of bands like this. This is the band diagram of a PN junction. Energy from P will go down to conduction band from P will go down to conduction band of N. Valence band from P will get connected to valence band of N. Sorry, this is V, huh? Okay. Is that clear? So, कोई बायस नहीं किया ना, नेचुरली तो ऐसा ही होगा. So since I have now bend, this is called band bending. What is it called? Band bending. As soon as I brought P and N together, and if their Fermi levels has to be aligned at steady state or rather equilibrium right now, no other force has been applied by me. This is equilibrium, thermal equilibrium. Fermi level must align. If they must align, the bands must get bent. Okay. Because for a PN junction, the conduction band is same going through, but it must show a bend near PN junction. Yes, Pawan. We have done this last time. Even if you have a gradient, the current flows, but there is a built-in field immediately stops it flowing. So because the net current is zero, you are not taking current out from there. So any time there is no current, we say dEF by dx is zero. we have derived that df by dx minus di by dx, this term has to vanish because there is no current. Okay. We have also said if the current flows, df by dx exists. That's how Fermi level will actually change. Actual Fermi level will show slope. That means there is current flowing across. Okay. In this case, no current. Fermi level must align. If that is so, this is clear to you. This is band bending. P bend like this, whereas band bend like this, and EI must be in between everywhere because EI is the midpoint level you have decided. So this is always 0.55 from your either side. Okay. However, EFN is close to ESN, EFP is close to EVP, and therefore this is called band bending. How much will be this, or even this, or even this? They are all equal. What will be this due to? Built-in electric field. The built-in energy related is 2V0. So the band bending essentially tells how much is the built-in voltage created. Is that correct? Larger the built-in voltage, steeper will be the bending. Is that clear? So if you have a smaller, now we want to calculate. How, on what quantities this V0 is depending on? Can you think on what quantity it will depend? This is a junction. The features are shown here. Only two things are meant to be, NA and ND. So V0 must be functions of NA and ND. Larger the NA and ND, will see, larger will be the voltage, smaller is NA and D, smaller will be the volt. Is that clear? So this is exactly, now we want to evaluate. So instead of evaluating EX, if I can directly correlate V0 to NA and D, then I will get the value. Though I can also evaluate, if I first evaluate electric field, I can integrate that and get my build. So two methods we can show they are identical either way. Okay. Okay. What is this W called? Depletion widths. Is that correct? Before we go ahead, let's say NAs are much larger than ND. What does that mean? For the same cross-sectional area, think of it what I said. If NAs are much larger means which junction I am talking now? Let us say P++ N junction I am making. Heavily doped N compared to lightly doped N, and I join them. Area is same, cross-sectional area for both sides is same. Is that correct? So for the same amount of charge to balance the N type, what should I get? Thinner XPO or thicker XPO? This is again, if the area is same, even in this itself, because the concentration is higher, area is same, smaller lengths are required to put the same number of charges there. Is that correct? So the depletion layer will be smaller in P side. Charge will be similar, but the thickness will become, because area is constant, area both sides is constant. Whereas depletion on N side will be larger compared to this. So what will it look like? I will show you this example. This will be something like, okay, this is negative and this will be positive. So larger the N, I make larger P plus, as if this will be a very sheet of charge here, and all depletion will occur in N counts, lighter ones. This is most important in device design. The depletion layer, so what is the voltage I said? Voltage is E dx, sorry, Ex dx. So if you have a larger base, most of the voltage will actually drop here, but actually, I will show you, this is what I want to show you. There will be an electric field which is of this kind, okay, and integral of this is essentially the voltage. So please remember, this depletion layer widths are decided by what? the dopings, larger the doping, smaller will be depletion, smaller is the doping, larger will be depletion. So this fact we actually use in, that's why we actually want to make P plus N junction. I want to have depletion all in N, okay, my device requirement. So I'll show you why I did that. Okay, now let's calculate. Okay, before we go for our convention, I repeat, I already said, if holes are moving in this direction, what is the direction of current? Hole current. This is convention I am using, which is standard convention. If electrons are moving here, electron current flows opposite. This is also given in book, so I thought maybe I'll show you. This is my convention. The direction of holes is same as direction of hole current. Direction of electron motion, the current is opposite to that of motion of electrons. Minus Q, opposite direction. Okay. This is my convention, which I just saw a figure, so I thought I should tell you. Okay. Now let's look at, before we quit, बोलो क्या इसको क्या बोलते हैं localized cell. Localized cell has a problem, it burns faster, because it has a smaller area, so large currents are drawn and finally it shuts off. So never try that. Sprayed. Today electrical engineering, the word is sprayed. Never try to localize. Anything you do localized, you are actually calling yourself a difficulty. ज़्यादा लोगों से बात करो. ओके, हम फिलॉसफी में बताएं थे ना, इसलिए बताया आपको. ओके, we already seen other day, if there is no current, Jn for example is Jn drift plus Jn diffusion is equal to 0. Let's say same for P. Maybe you can write Jp is Jp drift plus Jp diffusion is 0, because J is equal to Jn plus Jp is also 0, no current. Okay. Then we said that, just now I said, equilibrium, no bias, nothing happens, terminal constant, no currents. However, using this, I did derive, if you recollect, the built-in field is how much? Kt by Q, 1 upon, let's say there is a gradient in holes. Now let's say why I am creating gradient of holes. From higher P, I am going down towards lower P. From P in the P is very high, P and N is very low. So I am going from higher concentration of holes to lower concentration of holes. I am having a larger electron concentration in N and I am going to a lower concentration in P. So there is a gradient of holes and electrons I am creating. That's the figure I have drawn in. Okay. If that is the gradient, this essentially is what we derived. The built-in field is 1 upon Kt by Q 1 upon Px. Same way I can write for n kind. Ex for this, Kt by Q 1 upon Nx, dn by dx. Okay. Same equations. If I know this relationship, can you tell me, okay, let's say, can I rub this? Or maybe I can rub this. Okay, what is Ex can be written in terms of voltage? E in terms of voltage, gradient. E is minus dV by dx. So I want to solve this equation. So I say minus dV, okay, or you can also call plus dV, sign I will change the other side, dV, and let us say when I go from P to N, the voltage changes from Vp to Vn. Okay, let's say some potential at the edge of depletion there is Vp, somewhere here, okay, at this point some potential is Vp and some potential here is Vn correspondingly. So I integrate this Vp to Vn is equal to minus kT by Q. Then what should I write? Integral. From where to where I should integrate? No. Whole concentration at the edge of depletion layer is how much? P's of P. Holes. So this is P's of P and I am going to P's of N on the N side. Okay. 1 upon Px dPx. Is that okay? Is that okay? इन साहब ठीक है x को हटा दिया तो इंटीग्रेट किया. So now this essentially is saying Vn minus Vp is equal to minus kT by Q. Px का इंटीग्रल क्या होगा 1 upon Px का ln Px. Okay, and if I substitute the limits, what do I get? ln Pn minus ln Pp. Okay, take the signs correctly. Then I say V0 is defined as, please remember, V0 is defined as Vp minus Vn. Time is not very crucial because measurement is most important. Can be written as kT by Q ln P's of P by P's of P. एक साइन ज्यादा है पर ठीक है आपको डिफरेंस चाहिए आपको. You can define other way also. That's not very important issue. इसका माइनस एक आएगा ना. So how much is P's of P I wrote there? P's of P is Na. P's of N is Na square by Nd. So how can I write this? What should be the expression? Both Na and Nd now I have take. P's of P is Na divided by Ni square by Nd, which is equal to kT by Q ln Na Nd by Ni square. Is that okay? So V0 is essentially kT by Q ln Na Nd by Ni square. So can you tell V0 will be larger when either Na or Nd or both are larger. Larger the Na and Ds, larger will be the built-in fields. Is that correct? Now think of something interesting. Electric field is given by V by distance. Is that clear? Electric field is given by V by distance. If I want to increase electric field for the same V, or if I increase V and decrease D, then electric field will rise. Is that correct? So larger the doping, the electric field will also correspondingly rise. So the built-in field will start increasing as I increase Na and Ds. Is that correct? Minus Q0 is energy. So essentially there is an energy difference between N and P, Vn to Vp, and we say electrons are now you can see why I was saying that further electrons couldn't go. So let's say there were few electrons here. Okay. To go to the P side, what will they have to do? They must get at least this much additional energy to cross this. This is like a potential barrier problem. I have to climb. Is that clear? Electrons relatively can come down. Okay. But how many electrons are there on the P side? Very few. Very few. By same logic, holes can, opposite signs now, holes can actually go from P to N, but cannot go from, can't go from P to N, but can go from N to P. But that means very few holes can go from N side to P side. But larger holes now cannot move because they need additional energy to actually surmount a barrier to go the other way. So now if your applied voltage is such that it does not allow your carriers to go across, you have stopped carriers motion even if you applied bias. Is that clear? Even if I apply bias, if I do not allow carriers to get excited enough to cross the barrier, then there will not be any transport. Is that correct? So I must see that they must get excited enough that they can go over the barriers. Or what is the other possibility? If not over the barriers, okay, this is my triangular barrier. One method is it can go like this. Other is it can go here and then go, or it can go here. This is called thermal emission. This is called thermal plus field emission. And this is called field emission. What is field emission? Other name? Tunneling. Okay. So you have, one is thermal, picks up the energy and goes over the barrier. One it picks up some energy and then tunnels, so it's called thermo assisted by field. And then finally, even at the lowest of energies, it can go through. So there are three transport ways. Carriers can go from one side to the other. Is that correct? In most cases, we'll see which one will dominate. Tunneling is not. When is tunneling possible? If the barrier width is very small, that is the electric field is very large, then only carriers can field limit, which is not easy in most cases. So tunneling is unlikely phenomenon in most cases, but which device uses this? Tunnel diode, Nami and stuff, tunnel diode. So they actually allow tunneling. Okay. So let's see, next time, going ahead, we'll see further, is there any other way to derive this? Should be, because one method I said is this, other I can actually calculate fields and then integrate, okay, and we must get the same value. So we must get same value. We must also prove ECP minus ECN or EVP minus EVN is also QV0. Is that clear? The difference between the valence band must be built-in voltage, energy. Same is same is EI and EIP to EIN also should be QV0 because they are anyway midpoints, so they must be. So we must prove that the difference between EVP and EVN is also QV0 or ECP minus ECN is also QV0, same by EI. If we can prove this by another way, they are same, only trick on that. We will show that every time I connect P and N, I will create a barrier. I will create a barrier. Barrier is occurring essentially in which term it is coming? The drift is getting balanced by diffusion. Drift is getting balanced by, or diffusion is getting balanced by the drift, stopping it. Is that clear why a lot of money cannot be transferred? Because there is a huge barrier which does not allow you to give somewhere else. Okay. कौन पॉलिटिशियन है ना बीच में बैरियर है वही ले लेते हैं आपको नहीं मिलता ना so this is the reason why because this is natural you can see it's natural phenomena so we should not blame people because that's natural to take the money okay so we'll stop here